In the last lecture, we began examining one of three classes of reactions that we're going to look at in this chapter, right? We're going to look at precipitation reactions, acid-base reactions, and oxidation reduction or redox reactions. And at the end of lecture last time, we began looking at precipitation reaction. So, how can we predict whether or not a precipitate will form when two different compounds are mixed together in water? So for example, sodium chloride and silver nitrate as separate solutions, if you combine them, how would you know that you get a precipitate? Well, we can look at the structures for sodium chloride, silver nitrate in solution, right? Look at how the sodium, chloride, silver, and nitrate ions or interact with the water around it and see how that changes as these ions come together. The silver ions and the chloride ions come together to give silver chloride as a solid, right? We look at the structure and bonding of that, and the sodium nitrate remains in solution. But this requires understanding of bonding theory, and we don't have that yet. So instead, the only way you guys are going to be able to predict whether or not two compounds react to form a precipitation reaction is to memorize some solubility guidelines. So this is a table taken straight out of your book. I've decided to present the information just a little bit differently. If your compound has any of these ions, lithium, sodium, potassium, or ammonium, as a component of the ionic compound, it's generally going to be soluble. If it contains nitrate or acetate, same thing. So any compound containing any of these ions, you would predict, for the purposes of your test, that it should dissolve in water. Same thing for chloride, bromide, iodide, and sulfate. If they exist in a compound, they're generally soluble too, but with these exceptions. Right? We've already seen that silver chloride is insoluble. Same thing for the bromides and iodides. Lead in the 2+ oxidation state also compounds with chloride, bromide, and iodide are insoluble. Here's a curious ion we haven't met yet. The 2 here implies that it's a molecular species consisting of 2 mercury atoms that are bonded together to form a molecule, just like nitrogen or oxygen is N2 or O2, but the difference is that the molecule has a 2+ charge. So this is a molecular ion, a molecular cation. And so salts with chloride, bromide, or iodide are all insoluble. And then finally, the salts of sulfate are all soluble except for those of strontium, barium, lead 2, and the mercury 1 dimer. All right, so now on this table we're focusing on ionic compounds that contain these components are generally insoluble. So all the hydroxides, sulfides, carbonates, and phosphates generally are insoluble except for these exceptions. The alkali cations, lithium, sodium, potassium, as well as the ammonium ion, we've already seen that on the previous slide. All compounds that generally have these tend to be soluble. The new exceptions to this rule, right, for the insolubility of these compounds are calcium, strontium, and barium. Hydroxides are slightly soluble, and the sulfides are definitely soluble. Now keep in mind that our distinctions here of soluble versus insoluble, right, it sounds like night and day, but it's really not that sharp of a boundary. Everything will dissolve to some extent. And so what we define as soluble typically is a compound that will dissolve at least to 1 milligram per liter we take to be soluble, and if it doesn't dissolve to that amount, then we consider it to be insoluble. The other thing that you may have noticed as a pattern here, with the exception of sulfate, compounds that have anions with high charges tend to be insoluble, right? So sulfide, carbonate, phosphate, but not the sulfate so much. In Chapter 3, we were helped to organize our information in chemical reactions by looking at patterns in chemical equations, right? So we were able to see a combination reaction is two separate things coming together to form one thing. A decomposition reaction is one thing decomposing or breaking up into two or more things, right? And we looked at combustion reactions, which are reactions with oxygen that liberate a great deal of heat and usually light as well. Well, when we're looking at precipitation, acid-base, and redox reactions, we also can establish some patterns. And one of them is the so-called exchange or metathesis or double exchange reaction. You can think of this as partner swapping. So imagine compound AX consisting of two pieces, A and X. They could be ions, so A could be positively charged and X could be negatively charged. Same thing with formula BY. We can see a pattern here that A and Y come together and B and X come together. So we call this partner swapping. And it's definitely a hallmark of precipitation reaction. So let's show you what we mean by looking at an example. So if we look at a hypothetical reaction between a solution, aqueous solution of silver nitrate and sodium bromide, remember AQ implies that these compounds are dissolved in water as mixtures. Before you begin doing this partner swapping business, it's better to get a more detailed representation by what we mean by silver nitrate solution and sodium bromide solution. Written this way, we should not be thinking that the silver ions and nitrate ions are somehow stuck together in water. They absolutely are not. Remember in the previous lecture, we showed you how water can dissolve or surround each ion in the crystal and pull it away from the solid crystal, right? So a better representation for silver nitrate aqueous solution would be this. Okay, this is not to imply a chemical reaction, it's just another representation that these two components are separate. Where the silver ion is solvated by water and the nitrate ion is solvated by water. And the same thing is true for sodium bromide. So anytime you see an ionic compound aqueous solution, you should be thinking of the individual fragments that are moving around in water itself. This helps you think about what's going to happen as a possible chemical reaction, because if you have this material dissolved in one beaker and this material dissolved in a second beaker, and if you bring them together, well, you should be thinking that you've got four components that are all moving about in the same volume. And they're going to collide, right? Here's one possibility, is that the sodium ions and the nitrate ions collide and possibly form a precipitate, right? So we could write this here, sodium nitrate, and ask the question, is it soluble in water or not? Well, what do you use? Those solubility guidelines, and the general rules were, right, any compound that has a sodium ion in it typically is going to be soluble. Same thing for nitrate. So you would expect sodium nitrate to be soluble, so you would write AQ as a reaction product. But in truth, we haven't determined that an actual chemical reaction has occurred or not. What's important now is to look at what remains. You have the silver ion and bromide ions. When they come together to potentially form a compound, they don't remain in solution, right? So remember, the chloride, bromide, and iodide compounds are all generally soluble except for silver ion, lead 2+, and the dimercury 1 cation. So this precipitates out, and it is this which makes this chemical reaction happen. Imagine that this compound were soluble. What would you have in solution? You'd have four ions moving around, right? No chemistry whatsoever. It is the action of the precipitation that allows you to generate a product and drives the sodium and nitrate ions together as well. All right, so again, if both were soluble, no precipitate, no chemistry. If both were insoluble, well, you would have two precipitates, and honestly, then you would have a separation problem if you wanted to separate the two components. When describing chemistry that occurs in aqueous solutions in the form of chemical equations, there's three ways to write them. It doesn't matter whether you're looking at a precipitation reaction or an acid-base reaction or a redox reaction. You use three different equations to represent the information depending on what you want to focus on. The first one is the standard so-called molecular equation, right? So there's really nothing new here. We just write out the chemical formulas and what phase they're in. So this means we have an aqueous solution of lead 2 nitrate is reacting with a separate solution of sodium bromide and water, and when they combine together, we form precipitate forms, right? That's lead 2 bromide, and sodium nitrate remains in solution. Now, molecular is a bit of a misnomer. That's why I have this in parentheses, because none of these compounds are molecular. They're all ionic compounds. But at any rate, that's what we call them. Now, if you actually want to focus on the chemistry involved, you need to think about what species are actually present and that are reacting. In that case, we write what's called the total ionic equation. We can write it from the molecular equation. So if you write the molecular equation first, the total ionic equation represents the actual species present in solution and their numbers. So for example, for the formula lead 2 nitrate, there are three fragments, three pieces. One is a lead 2 plus ion, and we have two nitrate molecular ions, right? So don't be confused about the subscript 2 there, and now it's a stoichiometric coefficient there. We're just counting things, right? We've got three total. We do the same thing for sodium bromide. Now we have two formula units of sodium bromide, so we count two sodium ions and two bromide ions. We're essentially doing this in a manner it's consistent with a balanced chemical equation. Now we look at our products. We don't have lead and bromide ions in solution anymore. It's all present as a solid, as a precipitate, so that's how we write it. And then the sodium and nitrate are aqueous solutions, right? So we write the components as sodium ions and nitrate ions separately. Then finally, if we want to focus on the things that are actually reacting, we look at our products here. We see that it's going to be the lead 2 plus and the two bromide ions. Everything else, the sodium, the nitrate, on the left side of the equation and the sodium nitrate on the right side of the equation, we can see that there's no change. We call these spectator ions because they're essentially doing nothing, right? So if we filter out the spectator ions from our equation, right, they're represented in equal numbers on both sides, and we omit them not because they're not there, they certainly are. We're omitting them to sort of filter out and focus on the components that are actually doing chemistry. Then we have what's called a net ionic equation, right, which is just lead 2 plus ion plus two bromide ions generate one formula unit of lead bromide. Now, it's important to keep in mind that these three representations all describe the same chemistry. So the molecular equation describes the most compact representation for all of the chemical knowledge in a chemical reaction, right? You have your reactants, you have your products, all written out as formula units. Now, the total ionic equation addresses the question, what species are actually present in solution? Importantly, we find that on the product side, there are no lead and bromide ions present in solution. They've all precipitated out as a solid. Having done that, we're able to identify what the spectator ions are, and when we omit them or filter them out, we end up with what's called the net ionic equation. So the general procedure then for writing a net ionic equation is to first write a molecular equation, ask the question what's actually in solution, you write a total ionic equation, identify your spectator ions, then you can write your net ionic equation. Alright, so now let's go ahead and look at a problem to see how well you understand the previous lesson. So take a look at this, go ahead and pause it, the video, and then try to solve this on your own. Alright, so where do you begin on this problem? Well, you want to write a net ionic equation, so if you remember your definition for what that is, it's focusing on just those components that are involved in the chemistry. There's a shortcut that I'm going to show you first that holds true for ionic compounds. And then secondly, I'm going to show you a general procedure that will work all of the time, whether it's a precipitation reaction, an acid-base reaction, or a redox reaction. Focus on the product. Right? This is calcium phosphate, and so you can see that the components are going to be calcium, 2+ ions, and phosphate, PO4 3- ions. So we would write our net ionic equation like this. Start off with an arrow going to our product. You see our components, and we can identify what those are. All right? That's the quick way to generate your net ionic equation. So what's required here is for you to be able to look at a formula, pick out the polyatomic ions, remember what their charges are, and remember the charges for type 1 metal ions, or be able to deduce what those charges must be based on the charge of the polyatomic ions and the numbers involved. All right? So to show you the general procedure for solving this, what we would do is start off with a molecular equation. So we write down the species that are reacting, potassium phosphate and calcium nitrate, as aqueous solutions. And we know that one of the products is solid calcium phosphate. There must be something else, right? So we need to figure out what that is. So we can tell that to form the calcium phosphate, it's the calcium ion and the calcium nitrate that's reacting with the phosphate and the potassium phosphate. So the other thing is going to be the potassium and the nitrate, right? This is that double swapping. So here's our molecular equation. Now it's not balanced, so we have 2 phosphates on this side of the equation, so we need 2 phosphates on this side. So we put a stoichiometric coefficient of 2 there to count out the 2 phosphates. So if we look at what's going on here, we have our phosphates balanced, but the calcium's not. So we have 3 calcium ions, so we need 3 on this side, so we bring in a 3 here. Now let's balance with respect to calcium and phosphate. Now we just need to look at the potassium and the nitrates. Well, the potassium, we have 2 times 3 is 6 potassium ions. We have 3 times 2, which is 6 nitrate ions, so we need a 6 there. So now it's balanced. Alright, so our total ionic equation, we simply count out all the species that are present in solution. So we have 6 potassium ions, 2 phosphates, 3 calcium ions, 6 nitrates, going to the product, which again is calcium phosphate solid, so no ions on the product side for calcium and phosphate. And then we have 6 potassium and nitrate ions, again, because this is an aqueous solution. Now identify the spectator ions. Well, they will be the potassium and the nitrates, right, which are equal on both sides of the equation. And then our net ionic equation is what's left over, just as we had described earlier. So tomorrow in lecture, we will address your understanding of this section on precipitation reactions by looking at this exercise as well as these. The first dealing with solubility, and the second one where you need to apply your solubility rules to tell whether or not a precipitation reaction occurs or not.